Hello everyone, we are back at Women in Technology International. We are now sitting down with Dr. Santosh Kurinec.
Good morning.
Hello, good morning. Thank you for coming onto the show.
Oh, thank you for having me. It's been a real pleasure.
Yes, I'm really happy that you won your award last night.
Thank you so much. It means a lot.
And you're much deserving of it. So you are a professor at the Rochester Institute of Technology.
Yes.
And a professor of Electrical and Microelectronic Engineering.
That's true.
Yes.
Yes.
And a Ph.D. in New Delhi.
Yes. I did my Ph.D. in physics from University of Delhi in India. And now my research is sort of at the intersection of physics, electrical engineering, and material science. So when we combine all the three disciplines, we talk about microelectronics. So that's what I teach and that's what I do my research on. There are a number of devices that I'm working on. They go in your microcircuits and also they go on your rooftop. That means I'm working on solar cells to make their efficiency higher so that we can make energy cheaper in the future, more renewable. So that's the area I work and teach.
Material science, physics,
and electrical engineering
give us the ability to have chips inside of our phones and computers that make it process data very quickly, efficiently, and then the efficiencies are going smaller and smaller in terms of, is it both the distance between transistors?
Yes, exactly, that's what you're saying, very right. So basically when you look at any electronic circuit, let's say you open the back side of your computer desk, you see lots of wires going around, right? So when your chip becomes such a big, huge circuit, so there are a lot of wires. So you put them all in a very small volume. So a microchip is basically a conductivity architecture of materials. We put lots of materials, we change their conductivity. So we start with silicon, we dope it to make it P-type, N-type, and make all kinds of circuits. Then we connect the circuit with wires, all in a volume as small as less than 1 micron cube. And the distance between each transistor these days is of the order of nanometers. So you can imagine now, just imagine a skyscraper with the smallest room of the size of 10 nanometer. So you have billions of transistors in one chip. How do we make them? It's not magic, they are made out of periodic table. We are using silicon, phosphorus, boron, gallium, arsenic, copper, tantalum, tungsten. So we take all these materials, engineer them to make this device, which is really a marvel of modern technology.
Yes, it is. Oh, the way you're describing it is so interesting. What percentage is it silicon?
The substrate is silicon, basically. The starting substrate at the moment is silicon because this is the most predominant element, second most predominant element on Earth crust. It has the right band gap and we can make big crystals out of it. It has a diamond structure, just like diamond structure. And substrate is silicon, but we only use the top half a micron part of the substrate. Most of the devices go on top of it. So silicon is basically like steel for automobiles and aluminum for aeronautics. But there's a lot more materials on top of it. So we are also putting novel materials on top of silicon to improve the efficiency of the circuits. But that's a constant innovation and struggle that's going on. So that's what I work on, different materials, different configurations and different circuits, different ways of storing memory in the device so that your memory stays longer and you can put denser memory into your chips because data is expanding. You have a lot of information you want to store and that means you have to make your memory cells very small. And they should last long so that you don't erase your memory when the power is turned off. We call it non-volatile memory. So we are working on some of those areas. And we also are inspired by nature. Look at brain, how human brains store memory. We still remember our childhood memories. How do we store it? So we are trying to mimic, maybe we can make computers the way brain thinks. We can also make devices in such a way. So that's the areas that I work with my students, with my collaborators, all because the field has become so complicated that one person alone cannot do everything. You need expertise from different segments. So I work with computer engineers, I work with material scientists, work with product developers. So you have to work together to think of a product and we start doing research on it. That's what we work on.
I really want to connect you to Ahmed Amer, who we've had on the show, who's at Santa Clara University, who is doing data and memory and storage systems.
That'll be great.
Yes, because he was teaching us about if we transition our thinking process from this is our data to this is our memories,
as memory,
then that changes our relationship to all of this data because it's our memories.
Exactly.
Then also what you said earlier about silicon being to chips what steel is to automobiles and what aluminum is to planes.
Yes.
I thought that's really...
Oh, thank you.
Yeah, it's very good. It's very relatable analogy.
Yeah, we have seen more and more materials in our automobiles. We have the carbon nanotubes, carbon, and many other alloys are showing up. But there's always something base we can augment more, right? So we can always find more substitutes to improve the efficiencies. But some things becomes sort of standardized because they have the properties that we need. Silicon has a band gap of 1.12 electron volt, which makes it always remains in a stable state at the terrestrial temperatures. Like you can go to cold temperatures, you can go to hot temperatures, its performance remains good. So it's almost suited for 300 degree Kelvin on Earth. So, but if you go to automotive arena where the temperatures are say 800 degrees centigrade or so, then silicon may not work at those temperatures. So then we work with silicon carbide, another semiconductor that can withstand high temperatures.
Is this the same silicon that goes into our non-stick cooking pans, the very flexible ones?
No, that's a silicone. I think they use a different word for that. That's some sort of a polymer, but that's silicone.
So silicone versus silicon.
Yeah, silicon is an element, group 4 element.
Silicon is an element.
Yes.
Silicone is, what is that then?
It's a kind of polymer.
It's a polymer.
That's what I understand. I'm not perfect. I'm not.
Well, this is good. Now I have to go learn about this. So silicone is polymer, silicon is the element. And then you said silicon is ideal for chips because of is it conductivity?
Yes, it's a semiconductor. So pure silicon has higher resistivity. It's between insulator and metal. But when you dope it, when you put some sort of, say, some parts per million of phosphorus or boron into it, you can make it conducting. So since you can make it conducting...
Parts per million of boron.
Or phosphorus. Or arsenic, yeah.
Arsenic. And so any of these, just in very small quantities, enable silicon to start...
Yes.
Being good for conducting.
Yes, then it becomes a conductor of P-type or N-type. Then you can make diodes, P-N junction. You can make transistors, PNP. Or NPN, or you can make MOSFETs. So then you can make switches. Once you make switches, you make digital circuits. Once you make digital circuits, you can make logic gates, and that's how these circuits develop.
Okay, so once you make the transistors, then you can make logic gates.
Yes.
Okay, and then that would be the electricity flowing to one of these gates, and then the gate being opened or closed.
Yes.
And then that being how it processes.
It's 0 or 1.
0 or 1.
Yes.
And then is there a billion or a trillion of these gates?
There are billions of that, 30 billion in a modern chip.
30 billion gates in a modern chip.
Yes.
And it's all in this size of a...
They're all maybe 1 centimeter by 1 centimeter.
All
area.
1 centimeter by 1 centimeter. Oh,
or maybe some chips are slightly bigger footprint, and the height may be just few microns. So we put so much big circuits in the small volume. So that means that most of this development has happened because of the way that we make these devices. How are they made? They're made with photolithography, printing. So all the advances in optics and imaging has helped us make these devices. So we basically make layer by layer by layer structure. Just imagine this room. We have a rug at the bottom, and we have walls, and we have wires. So we will put first layer, then pattern it, then put second layer, then pattern it, then third layer, pattern it in such a way that forms that multi-level structure.
But how do you do that at the nanometer level?
That's the key. Nanometer level means we need to have optics that can shrink the sizes to that small. So resolution has to be very good. So there's a lot of development on photolithography, that means lenses and the wavelength of light that is used to create those structures. So a lot of research is on how do we pattern these materials. So patterning means photographic printing and then etching and depositing, then etching, depositing, etching, deposit, etch. So you have to do that at nanoscales.
So you etch into the silicon?
Yes.
And then you deposit the transistor?
Yes. What we do is we start with silicon wafer, and we dope it in the regions we want to dope, which are called the source and the drain of the transistor. So we selectively dope it, then we put gate oxide and gate metal. So that means you have to put oxide where you want to put metal where you want. So that means you have to have the patterning system in place, and then keep going and keep aligning it well, and then start wiring it to the back end. So it's a very, very elaborate process. So you need very modern fabs to do that.
Yes.
So most of the current fabs that we have, they are distributed all across the world. And typical investment in modern fab is about $10 billion. So, and you use wafers of the size of 300 millimeters, about pizza size wafers. So we take a pizza size wafer and we start making the chips. Then we cut the chips out from the wafer once they are made. Then we put it in the package. Then package is put on your device.
From the pizza wafer, that's where the
chips
are made. And there's a couple thousand of these pizza wafers in a fab?
Oh yes, they run 24/7 on an almost automated fabs. You won't see a human being. They are automated in such a way that they go from one step to another step in a robotic way. The wafers go from one footprint to the other footprint. You deposit a layer, you print it, you etch it, you deposit, you print and etch.
And just passes it along.
Yes.
And all in the size of very, like this small, very small.
Yes, each die on a wafer is a chip. So if you just imagine a pizza size, and maybe chip is of the size of your pepperoni, something like that. So you cut it, and we cut it, and then we package it. And that goes to circuits.
Yeah. Whoa.
So this chip has become very exotic these days. We make many chips. We sometimes stack them up and three-dimensional integration. It's like big cities, when it become crowded, you grow upwards. Yeah. So these chips are so dense now, we started to build in 3D integration, so that they can have more functionality at a small footprint.
Yes.
Yeah.
$10 billion for a fab. Okay, you were teaching me about this earlier. You were saying that the fabs, you like to ask your students about what makes countries able to have fabs.
Yes.
So $10 billion is a lot of money.
That's a lot of money. It can be a GDP of some nations. Yeah. It's a very high investment because technology is so advanced. It requires so many resources. And I believe that the place where you can have a good source of electricity, cheaper source of electricity, more access to water and transportation, because you have to move all this stuff to that particular place. Yep. So you need all those resources to build a fab, and a lot of investment goes into it. The most important is, even though I said they are mostly robotic, they're automated, but still we need workforce because you put so much investment into these machines. So we need very scientifically trained workforce for these to work in these. So that is our mission. I teach microelectronic engineering. We get students from all over the globe, and they learn. And someday I feel that they will go back to wherever they like to go back and create such fabs in the future, because we will be needing them.
We will.
Yes.
Yes, and we'll be moving into an era of lots and lots of devices in the future that are going to need microelectronics engineers, and especially them going back and stimulating their countries with fabrication center plants. So now, question about as we go into the even smaller, the quantum computing era. As we go past the nanometer even further down, what is about to be occurring in microelectronics at that quantum level? And
that's a very good question. We constantly think about it. We call it Moore's law, that we're making devices shrink. Every technology node is shrinking more and more, and we already reached about 10 nanometer node. And after that, we do feel that there's some bottleneck posed by physics. Every electron has a de Broglie wavelength. So once you reach the wavelength of the electron, you are limited. So therefore, beyond 3 nanometer, we will feel that challenge. So there are a lot of new ways of looking into it. Industry and experts are looking at quantum computing, where we can go to wave function overlap of single atom, and that's the era that is physicists are constantly exploring new ways of computing information for the future. But as I say, that 3D integration is another way of densifying your computer chip capability. If we can't go further in the XY plane, we'll go up in the Z plane. So those are the trends we are seeing.
Mm-hmm. So this is so crazy because quantum computing is also affecting encryption as well,
yes.
which is going to be crazy, especially with this proliferation of blockchain technology in the security era,
very
cryptography
so.
era, and now we have quantum computing as well. How are those going to jazz and vibe? How are we actually going to get down to past the 3 nanometer level? You said it was a problem with the electron, right?
Yes, I mean, we are relying on electron motion in our digital switches. So that means that
mm-hmm.
if you're confining electron in such small volume, we may not be able to really distinguish between 0 and 1.
Electrons in such small volume, it's hard to tell.
Yeah.
Okay.
So the next area that I'm still is area of my further studies, but we have to look into new solutions to go further. As security, it's not my field, but we really feel that every time human beings are very creative. If they find a way to do something, they also find a way how to make sure that it works. So there's more innovation involved in those areas in the future.
Yes, and yes. You've also done a lot of work in photovoltaics now. So
yes.
Has Rochester Institute of Technology collaborating with the University of
Central Florida and ASU. So since my experience is on semiconductor devices, which are made up of semiconductor and metal contacts, and solar cell is also a semiconductor device, but it's not as small as microchip. It's a big cell, it's just one diode. So it's just a big diode.
What's the size of a photovoltaic compared to a chip?
A typical cell these days, you can get about 156 millimeter by 156 millimeter monocrystalline silicon that is available in the market. And thickness is about 150 to 200 micron. So
and that's absorbing photons from the sun, mm-hmm. and then it's distributing that energy to the grid.
Yes. So the sunlight comes and solar cell absorbs the sunlight, and the photons from the sun, they give energy to electrons. So electrons jump to the conduction band, mm-hmm. and electrons and holes get separated. And when they combine, they gives the current to the output circuit. So that's how your electricity is used. So typically solar cells are these days in the market are close to 20% efficient. And in fact, just today there was an announcement that a company has made 24% silicon solar cell. So we see
24% efficiency?
Yes, 24% efficiency.
And that means out of the 100% energy from the sun that comes in, we keep 24%.
24%, yes.
And is that the highest so far we've had?
Highest on, I would say that at the manufacturing level.
Yep.
If I make a nice cell in my lab, I can get higher efficiency. But there's a theoretical limit to solar cell efficiency, which was posed by Shockley-Queisser initial theory that that's the maximum efficiency you can get. So silicon can give you about 28% maximum efficiency theoretically. But when you actually make a device on a production level, you cannot reach theoretical so quickly. It takes time to get manufacturing in place. But to get 20 to 24% is really a marvelous thing. And we have seen that happen very fast these days.
So we can put all of the solar tiles on our roofs and power the cars and the houses. And
mm-hmm. So it's a semiconductor device. It's a diode, but it's a big device. So since I work on microelectronics, very small devices, and solar cell, very big devices, there are challenges in both. Mm-hmm. To make something small and to make something big without any defect is also a challenge. But we work on it.
Yeah, it's interesting how you're going from both microelectronics with computer chips and also with solar cells and photovoltaics, and how those are larger on top of homes and versus the smaller in phones.
Yes.
So it's almost natural for you to be interested in both.
Yes, I think because semiconductor physics combines the two. It's the same physics that applies, but the challenges are different and the functionalities are different. But if you understand semiconductor physics, then you can relate to, you learn from each other too. So some concept we learn from microelectronics we can apply to solar cells. Some concept we apply to solar cells we can use in microelectronics. So we learn from each other that way.
Yes.
Yes.
I love that. Okay, and then do you think that solar is one of the, or maybe the most ideal form of free and sustainable energy for us, or close to free? Or do you think maybe nuclear fusion, mastering that, could be even better for society?
Yeah, that's a very good question. I often think about it, and I think based on my experience and my learning, we need an energy portfolio for every place. Not one form of energy can solve all problems. So I can imagine solar panels running your home electricity. But when I see the tractor trailers on the road and the amount of energy they consume, and when I see the big power plants and energy used in other areas, we have to have a balanced portfolio. So I think peaceful use of nuclear energy is a very good source of energy. And if it's developed in a reliable way, we have wind, and we have other geothermal, and fossil fuel we have to minimize because resources are finite, so we are relying a lot on sun. But one thing we must note, that in order to convert energy from one form to another, say chemical to mechanical, mechanical to chemical, or mechanical to electrical, we always need matter. So we need matter. So matter is also finite, right? So nothing is infinite, but we have to be very careful in using all these resources to be frugal with the use of energy. And that's what we should sustain. Energy is a big resource. I would say that watts, the power we talk about, is a very big resource that is finite, but we have to value that, and we have to find new ways of making an energy portfolio, balanced portfolio.
Yeah. There's I always wonder if we'll get to a point where me having something doesn't preclude someone else from having something, so we can have a society of ubiquity in all things. I always wonder about that, but matter is kind of one of the big variables in that equation. What are your thoughts on neuronal computing with neurons?
That's not my field somehow. I've not learned much about it, but that's something I should be looking into.
It's kind of interesting. We have a friend that is Ash Agabi, who's really starting to produce some interesting results in that field.
Oh, that's interesting.
Yeah, I wonder how similar, like if 86 billion neurons could compute.
Yeah, that's what I was mentioning to you about. We have to learn from how the brain works, how the synaptic connections. The brain works with a neural network system, whereas our digital computers work on a von Neumann architecture. So there are two different architectures. So we can learn from each other, and that's why a lot of computing people are trying to include neuromorphic computing in the algorithms, and that's the area that's going to grow. And I will make devices, they can make circuits.
Yeah. And we will continue highlighting your brilliances across the world. So how about we ask you just a couple questions on the way out? These are questions we ask on the show a lot. What do you think is the most beautiful thing in the world?
That's a very good question. And I think the most beautiful thing is that we have a brain that makes us explore, see, enjoy the world. And we have the natural desire to be curious and look at the nature, look at beyond planet Earth, and try to solve our problems as well as explore the universe. That's what I like.
Yes, I love that answer. Yeah, we're so grateful to be able to observe the cosmos and experience the cosmos and solve these problems and work together on this planet. How about, do you think we're alone in the cosmos?
Keeping my math hat and my statistics hat, I think that the probability that there is only one life is very low. I'm sure that there are many planets, many places which have the conditions like Earth has, or conditions such that another form of life can be sustained is very much possible. Someday we'll find them, or maybe they'll find us.
I look forward to that day so much. Yes, I want to be linked up with the cosmic sisters and brothers. How about, are we in a simulation?
That's a very, very philosophic question. And you know, being a material scientist, if I can touch something, I can feel something, I'm in reality.
Yes, it's a question that our show is named after because we like the thought experiment around it, because it gives us a better understanding of all of the variables that have to go into the world that we live in and into the cosmic structure and the evolution of what we live
I mean,
in.
as a human body is made up of basic chemicals like carbon, hydrogen, nitrogen, oxygen, and sodium, potassium. So, in other words, our body is a configuration. So, this configuration will last for a certain amount of time. And after that, these elements will dissipate back in the universe. So we have a finite configuration that we can make an impact to the world.
Yes. Santosh, I'm downloading my consciousness to the cloud as soon as possible.
Thank you. So nice to talk to you.
Thank you for coming onto the show. We greatly appreciate it. It's been a
Thank you
pleasure
very much.
learning from you.
You ask such great questions that makes me think even more. And so thank you very much.
We are very grateful to be learning about all of the incredible feats of engineering and design that are happening in both chips and photovoltaics. I mean, this is both tremendously important for the future of our world. So
amazing. Yes,
thank you very much, everyone. Thank you for tuning in. If you had a good time, make sure to share the content with other people. Make sure to go and create with this content. Don't just watch, but go and write. Go and make a video yourself. Go and talk to more people about it. Maybe start something in one of these fields. Subscribe, give us a comment below with your thoughts. Also join us on Patreon so we can continue coming to great places like Women in Technology International and highlighting the brilliance here. And we will see you soon. Thank you.
Thank you.
Thank you.
Thank you so much.